Uh, Hi all, we are here once again with our wind power technology. Today we move on to the fifth chapter uh, that talks more of economics of wind power systems. Actually, the fifth chapter is in two categories. We have the economics and then we have the environmental impacts. But this presentation will basically talk about the economics. The environmental impacts would come later. At the end of this presentation, it is expected that a student should be able to understand the factors that affect the generating cost of electricity, all of the factors. It is also expected that the student will understand economic appraisal, some economic appraisal indicators, and then it's again expected that the student will be able to, based on the knowledge of these economic appraisal indicators, assess the economic performance of wind power systems. By the economic performance, I mean to be able to tell whether a particular wind power investment makes financial sense or not. So that is basically what we would go through today. Economics of wind power systems. For a wind power plant, to be financially viable, it must do three main things. It must be able to produce energy, and then it must be able to last, long, at least up to the manufacturer's specified life of the turbine, and then throughout these operations, it has to be cost effective. It has to be profitable. And then the economic viability, of the wind power plant depends mainly on the cost of generating wind energy. Whatever the cost is, the operation maintenance cost, cost that goes to paying people and all that. All those things can be summed up into the cost of generating wind energy. And then after generating energy, how much does the energy cost, when being sold to the grid or sold to the consumer? So that is the market value of the energy produced. All the time for such an investment to make financial sense, the market value of the energy produced should be such that, the gains from that point should be far higher than the cost of generating the energy, so that there wouldn't be any financial losses. Now, the total generation cost for a wind turbine system, that is basically installed to produce electricity, is determined by these parameters. The wind regime, how much wind is blowing. Definitely, if there is more wind blowing, then there is more power, more energy will be produced, and more energy produced means there will be more energy that could be sold, for profit. So the wind regime is very, very important. And by the wind regime, our main focus is on the speed of the wind. Winds blowing at high speeds are much more favorable. It also depends on the energy capture efficiency, of the wind turbine. How much at each particular wind speed blowing, if the wind is coming to the turbine at a particular speed, what fraction, of that incoming, energy of the wind can the turbine extract, So the turbine has to be very efficient. And then the availability of the system. By availability, we are talking about the time that the turbine is available to produce power. So that throughout the life of the turbine, the time that the turbine has been shut down for maintenance and all that is taken out, and the total time that the wind turbine is actually available for producing power, that is availability. There has to be high availability. Most of the time the turbine would have to be available, to be able to produce power or energy. The lifetime of the system has to be able to last, and typically lives of typical wind turbine installations, range from about 20 to 30 years. Now that is the manufacturer's specified life. Although sometimes you could go beyond that, depending on how robust the design is. And then the generation cost also depends on the capital cost. How much money is invested initially into the whole project. Then how much does it cost for operations and maintenance, and all other costs, that are not mentioned in these categories. Whatever inputs may also affect the cost of generating electricity from a particular wind power plant installation. Now, the capital costs of wind energy systems. The capital costs, has to do with all initial costs involved in actually putting up the whole project, and it could range from wind resource assessment to purchasing of wind turbines, installation, engineering, and all that. And it involves the costs of all the various components at the initial stages of the project. Usually, the capital cost is usually measured in cost per kilowatt of. It's actually normalized, to measured in cost per kilowatt of rated power or cost per area of rotor diameter. So that if you have, let's say, typical capital cost of, let's say, $1,000 per kilowatt, of rated power for the wind turbine, then in that case, if you want to know the actual capital cost, let's say, of a 50 megawatts plant, just by multiplying the unit cost by the capacity, then you get the full capital cost of the whole installation. And normally, wind power plants are costed, in this particular way per kilowatt. And then the installed, as I've explained in the beginning, the capital cost includes all the costs at the initial stage, the resource assessment, permits for the land and various activities, installation, construction, engineering, road network, substation, instrumentation, and all that. All of these categories go into the capital cost of wind energy systems. Now, we also have operations and maintenance costs, that has to do with routine checks, the cost involved in routine checks, periodic maintenance, periodic testing, cleaning of the blades, and sometimes taking care of breakdowns, scheduled maintenance, so all these also go into operation and maintenance costs. They come periodically, definitely at a point in time. Some form of maintenance would have to be carried out, on the plants. So these categories of costs go into operations and maintenance costs. Then operation and maintenance costs is actually divided into two main categories: the fixed and variable. The fixed costs, operations and maintenance costs don't really change with respect to power generation. That's to do with salary given to employees and all that. That one is fixed. You would always pay that irrespective of whether you generate power or not. And you have the variable cost that has to do with the power generation and that. So we move on to economic analysis. Now, economic analysis is basically used to assess the profitability of a wind power project. To be able to tell whether it makes more financial sense to go into a project or not. Or to be able to help compare that particular wind power project with maybe a different investment, anywhere to tell which one would produce more profits over the other, or which one would be more profitable to actually go into than the other. And there are several different, models or ideas used to find out, or assess the economic viability of wind power plant. We have simplified models, we have the life cycle cost models, and then the last one, which we don't really talk about much, is the electric utility economic models. Our main focus will be on the first two, which is the simplified and then the life cycle model. Now, the simplified models are very simple to use, and they help the designer or whoever is doing the analysis, to be able to tell, within a very short time, how much profitable, this particular project would be, and in this particular model, the viability mostly depends on the cost of generating the wind energy and the market value of the energy produced. So the total cost of generating the power and how much is the power going to cost after generating. You compare these two, and then straight away you're able to tell if what you're gaining from the project is more than how much you put in. Then definitely you make profit. But if how much you put into the project is more than what you're gaining, then you definitely make a loss. So this has been explained in detail in the lecture material, where one main criterion used here is simple payback period. It basically tells how much time it takes for a typical investment to recoup the initial investment. So you put in money into a project, the project is also producing profit or income. So when you accumulate this income over time, how much time, within how much time frame would you be able to recoup what you put in initially at the initial stage? So the simple payback is given by the formula there, the capital costs per divided by the average annual returns, and the average annual return is expressed in terms of the annual energy produced over the annual energy produced times the price per unit energy. So when you substitute the relationship for the annual average return, then the simple payback period becomes the capital cost over the EA, which is the annual energy, and then the PE, which is the price per unit energy, or the price per kilowatt hour or megawatt hour, or the unit of energy used. So this is quite a very simple idea to be able to appraise, a project and tell whether it makes more financial sense or not. The only limitation to this particular method is that it takes the money, it considers the money in their raw forms. It doesn't really consider the time value of money, whether there is inflation, whether your amount is going to lose value over time and all that. It just looks at the money on the surface. You put in so much amount, and then annually you're making so much. So how much time would it take the profits, accumulation of the profits, to match up to your initial investment that you put in? So that is basically about a simple payback period. And then we go ahead to also express the cost of energy, as currency units per kilowatts or per unit of energy produced from the wind power system. And then the cost is expressed, the terms are actually defined in the lecture materials. You have the capital cost and the fixed charge rates, and then operations and maintenance, all these combined. Then you divide by the annual energy produced. I think this is quite, the formula is quite simple and clear to understand. Then we move on to the life cycle costing methods, and these methods actually consider interest rates and all, discount and inflation, time value of money, and all that stuff. So these ones give much more meaningful results as compared to the simplified methods that we talked about at first. As I've explained here, the life cycle is a commonly used method for economic evaluation of energy production system based on the principles of the time value of money. We all know that with time, if there's inflation, then with time the value of money will decrease. Because if you have some amount of money today, and there's inflation around the corner, what happens is that what you could use that amount of money to buy today wouldn't be the same as what you can use that same amount of money to buy in the next 5 years. Definitely, in the next 5 years, that same amount of money cannot buy what it can buy today. So that is what we mean by the time value of money. So in this particular methods, there are several parameters that could be used to appraise, the present worth factor, the net present value. Also have the levelized cost of energy, internal rate of return, and the benefit cost ratio. In other literature materials, in place of benefit cost ratio, you can also see cost benefit ratio. It's basically the same term, just that there's a reverse in how it's computed for. So look at the present worth factor. Now this idea is not too difficult to actually understand if you're familiar with series and sequence in mathematics. What happens is that when you have an investment, the present worth of an investment, at the end of the first year, it's going to give you some interest rates, and the interest rates is given as R. So what happens is that at the end of the first year, you have the present value, which is PV, being increased by the interest rates. So at the end of the second year, what happens is that what you have at the end of the first year is again increased by the interest rates, and then it carries on the third year, the fourth year, so on and so on until the end of the project, and it's expressed as what is given on the slides here. I think that there's another expression in the lecture material. So to actually find the future value, of the initial investment, at any year, let's say n, that is given by the expression the FV, which is the future value, is given by the present value, then into bracket 1 plus the interest rate, to the power, the raised to the power where n is the number of years. Now the present worth factor basically is given by the present value, the ratio of the present value to the future value, and that is what has been expressed there as the inverse of 1 plus r, to the power minus n. So it's like 1 over 1 plus r to the power n, and that is how I've expressed it on the slide. Because n is negative, it means the whole term is a denominator, so it's the inverse of the whole term that is here. That's quite straightforward. So whatever present value you divide by, in any particular year, you divide, if you want the present worth factor, let's say at the end of the 5th year or something, you just divide the present value of the investment or whatever to the value, future value at that particular year. When you divide by these two, the ratio that you have, that is the present worth factor. I must admit that at the first time some of these things could be a little confusing, but with time, and some constant reading, things will gradually sink in. I'll move on to the net present value. This one is mostly used. The difference between the time series of all cash outflow, the costs involved, and then cash inflow, that's the revenue you're making. So when you sum up the series of all these two, you find a difference, between the two. It gives you a net present value. And what happens is that the criterion should be such that the net present value should be positive. If it's positive, it means, there's time series of cash inflow, that is the income or revenue that you're making, overwhelms how much money you are spending on the cash outflow, and makes the investment a reasonable one. On the other hand, if the net present value is negative, then it means you're actually losing, throughout the duration of the project. You're actually losing value for money. So it wouldn't be a very good investment to go into. Or if it's zero, then it means you didn't really gain anything, you didn't lose anything. Whatever amount you put in, by the time of the project, you got back that same amount at the end of the project. So the relationship for calculating the net present value is expressed there. Bear in mind that the C here in this formula is a net. There's a difference between. It's not just it's a net cash flow, but the difference between the cash inflow and the cash outflow. Summed over the number of years of the project. And if there's inflation rate also considered, then the net present value relationship is modified here, just as is on the slide. In place of C, you substitute the expression of CJ here, then you get this. And I've explained here that the minimum criterion, for financial variability should be that the net present value should be a positive figure. Now we also have levelized cost of energy here. The levelized cost of energy, basically is the sum of the levelized annual cost, divided by the annual energy production. Then it has units of dollars per kilowatt hour. And this is basically used in utility-based calculation for the cost of energy. So it's basically a parameter that tells how much does energy cost per unit of energy or per kilowatt. The cost of energy, so that once you know this particular cost per energy that you are producing, then in selling this particular energy to the consumer, you need to go higher than this particular value that you have calculated for, in order to make some profit out of the project. Because any value below this levelized cost of energy would probably run you into a loss at the end of the life of the project. We also have internal rate of return, which is the discount rate at which the net present value will be zero. The discount rates, at which, and I've already explained that if the net present value is zero, then it means you didn't gain, neither did you lose at the end of the end of the project. So definitely, high values of the internal rate of return, is actually preferred. And this one even comes in, for instance, if you're comparing two projects, where you have the same net present values for each of the projects, then you might want to look into the one that has a higher internal rate of return. That one will fetch you more profit as compared to the other counterpart that has a lower value of the internal rate of return. And I'll explain here that the higher the internal rate of return is, the better is the economic performance of the wind energy or wind power plant. Then we have the benefit cost ratio, as I've explained in the beginning, that in other literature material you can see cost benefit ratio. If it's benefit cost ratio, then it's the ratio of the benefits to costs. If it's cost benefit ratio, then it's the ratio of cost to benefits. And the relationship is given there. The present value of all benefits, that is the income, divided by the present value of all costs associated with the project. And definitely this for the project to make more sense, the income should be more than the cost. Definitely, so this ratio should be more than 1. It should be greater than 1. If it's less than 1, then it means you're actually spending more than you're gaining from the project. So and higher values of this cost benefit the benefit cost ratio are actually preferred or desired, for the project to actually make more financial sense. So class, this actually brings us to the end of this presentation on the economics of wind power systems. Our next presentation on this same 5th chapter would have to do with environmental impacts of the wind power systems, of which we are going to look into next week. So basically, this brings us to the end of today's presentation. I'd like to thank you all for your attention, and then see you all next week. Thank you so much. Bye-bye.